Chemical bonding 3A, covalent structures. Lewis structures show the electron domains in the valence shell and are used to predict molecular shapes. Nature science we'll be looking at here. Scientists use models as representations of the real world, such as the development of the model of molecular shape, the valence shell electron pair repulsion theory, to explain observable properties. Gilbert Lewis, here seen in his Instagram profile picture, was the covalent bond guru who discovered that covalent bonds share pairs of electrons. Lewis structures, also known as electron dot diagrams, show the valence electrons of all atoms in a molecule. You can see here that you can draw two electrons, or you can draw a single line. Over here, for the double bond, you have two pairs of electrons, or two lines. These are called bonding electron pairs when they're found between the two atoms, because the electrons are involved in bonding, as are both pairs of electrons between the two oxygen atoms here. Alternatively, these ones circled in blue are non-bonding electron pairs, also known as lone electron pairs, lone pairs of electrons. You'll have to excuse the wind if you can hear it. I'm recording this during a typhoon. We need to forget grade 10. I'm going to use this following approach to draw Lewis structures. I'm going to read through this quickly. First, count all valence electrons, adjust for ions. Second, draw the skeleton structure, write the element of the central atom surrounded by the other atoms. 3. Make a covalent bond by placing a pair of electrons between the central atom and each outer atom. 4. Add pair of electrons to the outer atoms so that each one has an octet. 5. Add any remaining pairs of electrons on the central atom to give it a stable octet, or if there are not enough electrons to complete the octets, make double or triple bonds. Now that's quite a mouthful, I realise. So we'll do a few examples, but each time we're going to follow this stepwise, and that's what you should do. Learn to do this stepwise. So example 1, phosphorus trifluoride. So step 1, for the first example, count all valence electrons and adjust for ions. So the number of valence electrons in phosphorus is 5 here. Oh, I might get a different colour. The number of valence electrons, fluorine is 7. There's 3 of them. So add together 26 electrons. Your task will now be to place all 26 electrons around the atoms in the molecule or ion so that each atom receives an octet. Step 2. Draw the skeleton structure. Write the elements of the central atom surrounded by the other atoms. So there we go. Phosphorus in the middle with the 3 fluorine atoms. Step 3. We're going to make a covalent bond by placing a pair of electrons, and we'll signify it by drawing a line, between the central atom and each outer atom. And there we go. Got the 3 bonds in, so a pair of electrons, a pair of electrons, and a pair of electrons, which is 6. We've used 6 of the 26 valence electrons. Step 4. We're going to add pairs of electrons to the outer atoms so that each one has an octet. So, there we go. This fluorine here, for example, has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence shell. Okay? So, we've now used 24 of the 26 valence electrons. If you were to count all of the lone pairs and the bonding pairs, we'll come to 24. Now we need to add, for step 5, any remaining pairs of electrons on the central atom to give it a stable octet. And you can see here we've placed a lone pair of electrons. So now we've used all 26 valence electrons. All atoms have an octet. Well done. Let's do another example. CH2O, methanol. Count all the valence electrons and adjust for ions. So we've got 4 valence electrons in the carbon. We've got 1 valence electron in each hydrogen, so 2 of them. And we've got 6 valence electrons in the oxygen. Add them together, 12 electrons. Our task now will be to place all 12 electrons around the atoms in the molecule or ion so that each atom receives an octet. Step 2. Oh, there's the wind again. Oh, mercy. We'll draw the skeletal structure. Write the element of the central atom surrounded by the other atoms. So there we go. We've got carbon in the middle. Step 3. Make covalent bonds by placing a pair of electrons between the central atom and each outer atom. There we go. We've now used 6. 1, 2, 3, 4, 5, 6 of the 12 valence electrons. Step 4. Add a pair of electrons to complete the octet of each outer atom except hydrogen. So we've got the lone pairs on the oxygen here. 1, 2, 3, 4, 5, 6, 7, 8. It has an octet. We've now used 12 of the 12 valence electrons, but we're not quite finished yet. Why not? Can you see something a bit odd with the carbon? We've got to give the central atom an octet by making a double bond. So one of the lone pairs here will move over and form a double bond here between the carbon and the oxygen, or get involved in a double bond, should I say. So you've placed all of the valence electrons on all atoms. Let me say that again. You have placed all of the valence electrons and all atoms have a stable outer shell electron configuration. Great. Example 3. We're going to count all of valence electrons, and this time we're going to have to adjust for ions because you can see it has a charge of 2 minus. So carbon, 4 valence electrons. Oxygen, 6, and there's 3 of them, and a charge of 2 minus, so it must have an excess of 2 electrons. There's the 2 electrons. 24 electrons. Our task, should you choose to accept it, should we choose to accept it, is to place all 24 electrons around the atoms. Step 2. Draw the skeletal structure. Write the element of the central atom surrounded by the other atoms. Carbon there, surrounded by the oxygens. Step 3. Make a covalent bond by placing a pair of electrons between the central atom and each outer atom. There we go. We've got bonds now. So 1, 2, 3, 4, 5, 6 electrons involved there. We're going to add a pair of electrons to complete the octet of each outer atom. And remember that we've got 18 electrons left. Okay. So this oxygen now has 8. This oxygen has 8. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8 has 8. Fantastic. So we've used 24 of the 24 valence electrons. Now we can see that the carbon only has 3 bonds, so we're going to give the central atom an octet by making a double bond. There we go. And you've used all 24 valence electrons, but we're not quite finished, are we? It's a polyatomic ion. Now this is a very important step that people often forget to do. You need to put square brackets in and add the charge around the Lewis structure for polyatomic ions. You mustn't forget to do that. Okay, can you try these please? Press pause and have a go. There we go. I apologise. I apologise for the rogue slide. Formal charge. This is for you HL students only. Sometimes it's possible to draw 2 or more Lewis structures that obey the octet rule. Which one is correct? Chemists use an approach called formal charge to help determine the most appropriate structure, and there's a very easy formula to use. Formal charge equals the number of valence electrons minus half the number of bonding electrons minus the number of non-bonding electrons. So let's look over here. The formal charge on carbon has a valence, number of valence electrons, 4. Half the number of bonding electrons, 1, 2, 3, 4. So it's going to have 8 because there's 2 in each. So half multiplied by 8. Number of non-bonding electrons, it has no non-bonding electrons, so 0. And this comes to 0. Let's look at the bromine. Bromine has a valence electrons 7. It has single bond there, 2 electrons, so half multiplied by 2. And it has 1, 2, 3, 4, 5, 6 non-bonding electrons, so 6 here. You do the math and you get 0. Let's have a look at these then, okay? The carbon here has valence electrons of 4. It has 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, multiplied by half, and it has no lone pairs or non-bonding electrons, minus 0. Oxygen, single one here. Oxygen has 6 valence electrons, 6. It has a single bond, so 2 electrons, half times 2, and it has 1, 2, 3, 4, 5, 6 non-bonding. Do the math, you get minus 1. The double bond, again oxygen has a valence electrons of 6. This time it has 4 electrons because it's a double bond, half times 4, and you take away the non-bonding electrons, 1, 2, 3, 4. Do the math, it equals 0. Nitrogen, valence electrons 5, bonding electrons 6, multiplied by half, and you take away 2 as it has 2 electrons, non-bonding. Next, a fluorine, we've got valence electron 7, we've got one bond, one single bond, so 2 electrons multiplied by half, and we've got 1, 2, 3, 4, 5, 6 non-bonding. Do the math, 0. To choose between 2 possible Lewis structures, you look for structures that have the formal charge, have a formal charge difference closest to 0. And you work that out by the maximum formal charge minus the minimum formal charge. Okay, the difference between the two. Secondly, the one that has the negative formal charge on the most electronegative atoms. Let's have a look. I want you to have a go at this. Draw 3 possible structures for the thiocyanate ion. Okay, then find the formal charge on the atoms in the 3 structures and select the most appropriate structures according to formal charge theory. Press pause and really have a go at this. Have a good think before skipping forwards to see the answer. Okay. So these would be the 3 structures. You can see we've got on the left here single bond sulfur carbon, triple bond carbon nitrogen. We've got 2 double bonds here, and we've got a triple bond sulfur carbon, a single bond carbon nitrogen here. I'm going to do the math quickly. Okay, so we've got valence electron minus bonding electrons minus lone pairs or non-bonding electrons. Okay, and you can just check the math there for me if you want. So which one, according to formal charge theory, would be most prevalent? Well, this one's going to be rather unlikely. To start with, it has a positive charge on one of the atoms, and it has a high formal charge difference. You've got +1 and -3, so an overall difference of charge of 3. This one here would be the most likely according to formal charge theory, because nitrogen is the most electronegative, and there's a small difference in formal charge, just -1, and the nitrogen has the -1 on it. Okay, oh, the pen didn't work, never mind. This one here, you can see the sulfur is -1 over here. The nitrogen is more electronegative, so this one. Okay, there are exceptions, and we need to take note of these. Sometimes the central atom in stable structures do not have an octet. First, look at atoms with less than 8 valence electrons. Molecules containing a group 2 or group 13 central atom can be found with less than 8 valence electrons. One example would be boron trihydride. The number of valence electrons here is 6. This here is the structure, so there's single bonds between the hydrogen and the boron. The boron has 3 valence electrons, and each hydrogen is sharing a single electron, which comes to 6. All 6 valence electrons are being used, and the central boron atom only has 6 valence electrons. So what's going on? Why is this possible? Well, let's take boron trifluoride as an example, and think about the 2 possible structures. We're going to use a formal charge theory to determine the most appropriate structure. Do the math quickly. Boron has 3 valence electrons, and fluorine has 7, and it's 3 of them, so there's 24 electrons. Quickly draw out the possible structure. We've got boron with single bonds, and we've got fluorine with 1, 2, 3, 4, 5, 6 6 non-bonding electrons, and it's also got the 2 bonding electrons. The formal charge on boron, do the math quickly, is 0. And fluorine, 7 valence electrons minus, it's got 1 bonding, so 2 bonding electrons multiplied by half, and it's got 6 lone pairs, not 3 lone pairs, 6 non-bonding electrons, and so it equals 0. Conversely, if we did this, if we moved one of the lone pairs in to give ourselves a double bond, then boron would indeed have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. It would have a full octet. However, when we do the math, you see that the formal charge on boron is -1. The formal charge for the fluorine, the single bond, is 0, but the formal charge on the fluorine here, the double bond, my pen isn't working for some reason. Is +1, and structure 1 will be preferred because it has a formal charge difference closest to 0, and structure 2 isn't appropriate because one of the fluorine atoms has a positive formal charge, and remember, fluorine is the most electronegative atom. Okay, let's have a look at some other exceptions to the octet rule. Atoms with more than 8 valence electrons. This occurs in molecules that have 5 or 6 atoms bonded to the central atom. An example would be phosphorus or tetrafluoride. How many valence electrons does it have? Phosphorus has 5, fluorine has 7, and there's 5 of them, so altogether it'd be 40. There's a quick sketch of it. You can see that phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What? So we have used all 40 valence electrons here. Okay. The phosphorus atom has 10 electrons, 10 bonding electrons. So why does phosphorus have these 10 valence electrons? What's going on? I'm sorry. Well, it has an expanded octet. And it only happens with atoms that have empty d sublevels. Now, what do we mean by this? Let's have a look. If we consider the electron configuration of phosphorus, we've got 3s2, 3p3. Now, think about the valence shell electrons here. If you draw it out, you can see here that the 3p orbitals could each make a bond. So 3 bonds are possible. However, if we promote this electron here, oh, a little red one appeared. You can see now 1, 2, 3, 4, 5. We're able to make 5 bonds. 5 bonds are possible because of the electron promotion into the 3D sublevel. HL students, there isn't an additional step that you learn about later on to do with hybridization. Okay, let's now take a look at coordinate or dative covalent bonds. Remember, covalent bonds involve the sharing of an electron pair. You see it down here. Sharing is caring. Usually each atom provides 1 electron to the shared electron pair. In a coordinate or dative covalent bond, both electrons in the shared pair are provided by 1 atom. An example here, NH4+. Ammonia reacts with a proton to give us NH4+. What's happening? The lone pair on the nitrogen is donated to the proton. The H+ ion or proton has an empty 1s orbital, and so this lone pair can go in and fill it, and you end up with a structure here, and it's positively charged. You see, this is positively charged. So in the new NH bond, both electrons in the shared electron pair are provided by 1 atom, by the nitrogen. Often or sometimes an arrow is used for a dative covalent bond, you can see here, and the arrow points towards the atom that received the electron pair. You need to know that these molecules or ions have coordinate covalent bonds, and you've got to be able to draw them too. So let's have a look at H3O+. You can see we've got the lone pair in there, and the other lone pair is being donated or shared with this hydrogen. Okay, and you draw in the arrow, remember your square brackets and charge. And in carbon monoxide, you've got the oxygen sharing one of its lone pairs with the carbon.